Hello everyone, good afternoon. I'm just waiting for the attendees to arrive and we'll begin the webinar very shortly. Just a few moments. Okay, good afternoon everyone. Welcome to this webinar on how to classify non-ATEX rated equipment. Today we'll be dealing with specifically the procedures and the assessment methodologies commonly referred to as non-electrical equipment ignition risk assessments, referred to as a NIRA. It is a way to achieve compliance for non-ATEX or legacy ATEX equipment. Go ahead to the next slide. So here's the objectives of our webinar today. So we have a brief introduction to ATEX, DESIR equipment, using the standard, which is the ISO 8079-36. So this outlines the methodology for, in essence, the risk assessment methodology for designating equipment or certifying equipment as safe for use in a hazardous zone. So we'll go through the assessment procedure. So typically what I would do if I want to undertake a NIRA, and includes just a very basic work example for mixer unit. So it would be very exciting. First, I'd just like to go through about our company, Sigma-HSE. We have a presence in the UK, India, Asia Pacific, and now the USA. We primarily focus on process safety consultancy, laboratory testing, as well as training among a wide range of process safety needs. We bring together experts from around the world to achieve the process safety requirements. For example, achieving compliance with regulatory compliance locally where you are. We also undertake laboratory testing. So this is like, for example, your onset temperatures, your flammability data, your explosion severity data. It's quite relevant to today's topic because with these testing data, you could find and ascertain the correct equipment. So for example, temperature class, the maximum allowable temperature, or be it in, say, dust form or in vapors form. Also explosion severity. So when you buy your explosion panels in your dust collector, for example, it is suitably rated to certain values. For example, a maximum pressure rating, a KST value. And yes, so we offer a range of consultancy services. More specifically, yes, Desir, ATEX, Hazardous, which is process hazard analysis. We also operate in the field of functional safety and chemical reaction hazard analysis, which is also a very interesting aspect to process safety. Also, we have numerous webinars on these topics as well. So regards to our laboratory testing, we have a range of equipment to provide flammability data, different properties we can ascertain, as well as the electrostatic properties. So typically flammability data, as I mentioned, like onset temperatures, say for your chemical reaction hazards, as well as a wide range of testing, such as minimum ignition temperature for dust clouds, as well as layer ignition temperature. Some of these values in this testing is actually needed and is used in our risk assessment for this NIRA that we'll be talking about in today's webinar. So first of all, I'd like to talk about the first steps of undertaking a risk assessment. So this is basically a very basic overview of the Desir ATEX assessment, and then finding out more about the ignition sources, what they are. So yes, in a typical ATEX or Desir assessment, typically have 3 steps. First step is to find out where your flammable atmospheres are. So this is the hazardous area, which is the zonal classification. So for example, you have a natural gas pipeline. You find out that in the flanges or the pipework fittings, it could leak. It could form a hazardous area. This is the bubble, how big it is. So is it 1 meter distance, half a meter? That is your flammable atmosphere. That's step 1. Step 2 is to identify the ignition sources. So typically these can be equipments, it can be items, it can be metal plant, it could be personnel, it could be even the process that generates the ignition source. So typically there's 13 types of ignition sources in industry, but 4 are most common, which is hot surfaces, electrostatic discharges, mechanical sparking, and unsuitable electricals. And then once you find out that, then the third step would be to have a base of safety. So how you control against ignitions, potential ignition sources becoming effective. So typically you can have ATEX rated equipment, you earth all metal plants, or you have an earthing system in place in these hazardous areas. Or as I mentioned here, replaced with ATEX certified equipment. Or you can undertake a risk assessment to designate them safe for use in hazardous areas. And this is the topic of our webinar today, the risk assessment methodology, the standard, the procedure, and some learnings. As well, I'll be sharing with you my insights and how to undertake it. So we will have a worked example in this webinar. Go on. So yes, so how to classify non-ATEX rated equipment, which more specifically is how to designate them safe and what methodologies do you use. So what is the standard? So the standard for this particular risk assessment procedure, which is a technique, is the 8079-36. It's a formal process used to determine the EPL, which is the equipment protection level, which is the same thing as a category, which comes in category 1, 2, and 3, which corresponds to the hazardous zone, the zonal classification, which again corresponds to the frequency. So typically, if a flammable atmosphere is occurring continuously, it'll be a zone 0 if it's vapors, or 20. Now, if it happens as part of normal operations, just intermittently for a short time, then it's usually a zone 1 for vapors, or 21 for dusts. So this is typically something that's being poured just for part of normal operation, like you're filling the manway of a reactor just for a short period of time, but you do create it intentionally. That's like a zone 21 or a 1, depending on the materials used. And the other category is category 3, which is the less riskiest. It's less risky because it appears less short amount of time. So it's more like abnormal conditions. So something leaks or something there's an abnormal, like a spill or rip, or like in a dust collector, your filters can rip and it can lead to a carryover of powders. So it's an abnormal condition. It doesn't appear so much. It doesn't appear frequently. So yes, so this is the process. So this risk assessment methodology in this standard outlines the procedure to achieve the correct EPL and then show that your equipment is safe. There's different types of protection, like A, B, C, D to H, and type H is the formal methodology is referred to as a type H protection. So sometimes when you see an ATEX rated nameplate, say for example your motor, it will have EX, it may say type E, which is type of protection level. So this is the H, which I'll explain further in the webinar. So this standard is predominantly used by designers of new equipment, so manufacturers, but it can also be used as a basis, or the methodology can be used to assess legacy equipment, so pre-ATEX, so that's before July 2003. Also to note, that's the installation date. And depending on the category, which is the zone or the area that it operates, you can actually use it post 2003. Although the good practice is to have usually replaced with ATEX rated equipment if it's after 2003, but you can use the same methodology for equipment if it's installed after 2003, if it's category 3, or there can be special circumstances. For example, I've experienced in the pharmaceutical industry, it takes a lot of time it takes many years to get a qualified piece of equipment that goes through validation, and so sometimes the client has found out that it is using flammable materials. So instead, although it's not legally compliant, you can still undertake this risk assessment and show that it is safe or designate it as safe, but although not certified safe, designated safe. Just thought to mention that. I don't think you can see it, but there's a risk assessment table on the side and the bottom right, but we'll talk about this more in the preceding slides. So in essence, the standard outlines a methodology. It's basically it has 3 steps as I find it from my experience. It's in essence very similar to some tables risk assessment tables that you might see in other types of risk assessment methods, like in a HAZOP or a hazard or a SIL or LOPA. You typically outline the cause, the scenario, and then you put the safeguard, and then you have that risk level identified. So in this case, as mentioned in the standard, your first step is to identify what type of ignition sources there are. And then the next step is to put in the scenario and the reason why they've been considered. So for example, as I mentioned, there was 13 types of ignition sources that are most common in industry. 4 are most common, but in NIRA's, there's non-electrical equipment ignition risk assessment. We don't take account of unsuitable electricals, because they have, for electrical installation, as electricals as an ignition source has their own standards and their compliance. So we can only realistically or usually look at the 3 types of ignition sources, which is hot surfaces, mechanical sparking, and static electricity or electrostatic discharges. So yeah, so step 1, identify the types of ignition sources. You put it in a table, and the step 2 is outline the scenarios for each ignition source type. So for example, hot surfaces, a scenario could be during normal operation, you have a bearing, it's rotating, and there's also a static part. So that's getting hot, that's generating heat. So that's one scenario. And there are many types of scenarios. So the bearing could get hot during normal operation, it could deform, and then it could lead to a misalignment of a shaft inside this rotary equipment, and possibly the shaft could even break off. So there's 3 different types of scenarios that are outlined, and each scenario, as mentioned, step 3, will need a safeguard. So your safeguard could be, usually it's like can be procedure, maintenance procedure, it could be instrumentation like temperature monitoring, vibrational analysis, sensors, or even inadvertent sensors can be used in an equipment. But I will talk about this later on in the slide. So as I mentioned, when you do your ATEX Desir assessment, or ATEX or Desir, you have a zonal classification. So it could be zone 0, 1, 2, or 20, 21, 22. That corresponds to an EPL. As you can see, GA, DA is for zone 0s and 20s, and the less risky or the less onerous is the 2s and the 22, which is the GC, DC, which is also category 1, 2, 3. So category 1 is the GA, DA. And for each hazardous zone, zonal classification type, you have to consider the scenarios where ignition sources can be effective under 3 types. So normal operation, it could be expected malfunction, which is the zone 1s and 21s, and then it can also have to also consider rare malfunctions. So an example of these types of malfunctions, so it can occur in normal, expected, and rare malfunctions. So if I was assessing, for example, an equipment like a screw conveyor, and its zonal classification was only, say, a zone 22, you only have to consider scenarios for normal operations only. Each type of malfunction has its own types of scenarios. So what is a rare and expected malfunction? That could be something snaps, something breaks. An expected malfunction could be like the thermistor fails in a motor, and if the external motor fails, it could generate heat and then transfer the heat through the shaft into the blades. So that's just an example. I'm getting a bit micro level, but go on. So yeah, here's a typical examples of scenarios for what is rare and what is expected. Again, this is all outlined in the standard, the guidance. This is probably the tricky part of this assessment. Understand what scenarios to consider. Is it credible? Because when you fill in your table, you have to give a reason why you've considered it. So, for example, you might have an expected malfunction, say, for example, trapped metal ingressing into your dust handling system, and then you have to give a reason, and then you have to justify what are your safeguards. For example, you may have an upstream magnetic separator, you may have procedures in place, like a strict GMP environment, or there's some practices. So what I want to say is that this is the trickiest part of this of the risk assessment, and of course these are just some examples, but there are more examples and they're more complicated ones as well. So just have awareness of this. So here is an example of a category 1 equipment. It's a mixer. I believe it handles so flammable vapors as well as flammable dusts. So as you can see, this is the typical safeguards that you have for the three common ignition sources. So vibrational monitoring, welded impellers, solid shafts. I could probably add, I've seen mixers where they have in their manuals it states how to maintain an equipment. So this specific mixer is an example, it's a hypothetical example, but it's very close to something that we have done ourselves or looked at from a NIRA perspective. And yeah, so this is the type of safeguards you typically have. Although because it's category 1, it's usually a zone 0, zone 20, so it's a more onerous, higher level of risk. So you must consider. So these safeguards are used it's used as a safeguard for the rare malfunctions. For example, like the shaft of this blender breaking off. Okay, so what safeguards you have? You have vibrational monitoring. You may have maintenance procedures in place. So say, for example, check the bearings every so often at regular intervals, check for trapped powders. Maybe there's some sort of thermography temperature monitoring, which there are, say thermocouples on the bearings. But this is just to give you an example of level of integrity of the equipment that you have for ATEX rated equipment. So whether I also just want to add, so when you do buy an equipment and it's ATEX rated, it has an EX plate, the manufacturer has also undertaken this same risk assessment outlined in this methodology, this standard 8079-36. And then from there, it's lodged and sent to a technical authority that confirms it or verifies it. And then you get the EX plated on your equipment. So yeah, these are just some examples of what a thorough ATEX rated equipment for a complex machine like a mixer handling hybrid flammable materials. So I like to go through the NIRA assessment process. So this is typically what I would do if I were to undertake this risk assessment to classify, designate safe, or self-certify my equipment that is not ATEX rated. So yeah, so step one, you generate your hazardous areas, your zones, zonal classifications, find out what equipments they are. So you have a spreadsheet. You can assemble plant equipment, have the relevant flammability data. So for example, sometimes you'll need a range of flammability data, but as an example, you could have ignition energies as well, minimum ignition energy. Maybe the minimum ignition energy could be very, very high. So maybe you can discount or not consider certain ignition sources. For example, the MIE of a certain dust could be more than 1,000 millijoules, and therefore you may not need to consider mechanical sparking or spark discharges, as an example. And the key point is, so the key point after this is to go look at the equipment. So there's one thing doing it. We don't usually do NIRAs as a desktop. You have to go there and look at it, inspect it, then identify any inherent ignition sources. So for example, maybe during the inspection, which doesn't necessarily need to shut off the equipment, but just like to look at the main contact elements. So for your blades, your impellers, you might identify rust, you might identify loose bolts, which again, you'll use in your risk assessment table. So this is step 5 now, conducting the ignition risk review, the NIRA. You conduct it and it will come back with safeguards or gaps in your safeguards. So then you might need to apply the new procedure, measures, or safety functions. So this can be, as I said, like temperature monitoring. Maybe you need to have a maintenance schedule, an updated maintenance schedule, maybe things that need to check or specifics needs to be improved. Maybe there is no check for I don't know, the liquid level in your lubrication systems for a rotary equipment. There we go. So when you go on site and you have to look at the equipment, you usually have a team requirement. So the assessment team, the lead facilitator, a person with understanding of the plant area classification. You may need the equipment manufacturer sometimes, because sometimes the manufacturer has access to intimate knowledge. Maybe they all know the materials of construction, if some things may not be stated on the manual or the equipment manual. Again, you'll need to know, you have a person with the knowledge of the equipment, history from experience, the maintenance procedure, and any previous failures. So the important thing that when I undertake NIRAs is this historical experiences. So in the more complex equipments like your reactors, which handles flammable vapors, I've done jobs where the experience really helps, and especially when they want to find out about bearings or if there's any loose bolts, or because from experience they considered this as a potential ignition source, like say not smoldering dust, but say smoldering as a potential ignition source. Because you have that experience now, you can put that into risk assessment and then apply the new safeguard if there is a safeguard, or maybe there isn't a safeguard. So in this specific example, I want to recommend them for this reactor, this agitator, to do undertake maybe more pressure drift testing. So like a pressure testing of equipment before each batch. So just to make sure the bearing isn't being destroyed or deformed. So it really helps that having that knowledge of equipment, especially the person handling it. Yeah. So typically in the NIRAs, what can be assessed? The NIRA is an assessment technique. It usually is applied to mechanical equipments. So previously, NIRAs was referred to as mechanical equipment mirrors, so mechanical equipment risk assessments. But they've changed the name of it now. It's become non-electrical equipment ignition risk assessment. So now it's become more broader. This is when they changed the standard, I think in 2016. So yeah, typically we apply NIRAs for mechanical equipments, but the same methodology can apply to not mechanical equipment, just anything that's not electrical. So it can be even just say it can be outsides of, it can be motors. Technically, it can be even solenoids, even valves. So yeah, this is the first step. So usually it's like fans, extraction fans, mixers, belt conveyors, mills, conveying systems, serving units, pumps. So, and a majority of these equipments on the list is like dust handling equipment, but we do it for vapor, so flammable liquid handling equipment like the pumps, compressors, any valves in that as well, reactor agitator, that's quite common. So yeah, as I mentioned, it can also be low risk equipment. So the same methodology can be applied into valves, maybe dampener valves, maybe just simple. It can be relatively simple equipment like pneumatic valves. I guess this is when it mentions pneumatic valves. This is much more to do with vapor environments. Usually in dust environments, you can get away with, if it's legacy, if it has ingress protection. So it's easier to protect against like dust ingress. But whereas if it's vapor environments, they have their own level of sealing protection that you needed. So it's something to consider. And also to note that sometimes undertaking NIRAs would mean you have more focus on your maintenance procedure, and it's much more closely scrutinized. But there might be some equipment, say for example a small solenoid valve, it's better to replace it with the ATEX rated equipment in terms of costs than to undertake a NIRA on it if it's just easier. So that's one benefit. But of course, if you want to take a NIRA for large equipment like a screw conveyor or your a blending unit, typically ATEX rated equipments are usually 3 times more expensive, just a rule of thumb, than non-ATEX rated equipments. That's not to say that you shouldn't buy ATEX rated equipment. Of course you should, that's the legislation, but I've just thought just to mention that out. Good practice is to always get the ATEX rated equipment. So yeah, so I'm beginning to do my NIRA assessment. First, you have to collect a lot of information about the equipment. So typically this is the manuals, the drawings, and especially the speeds of the moving parts. So the speed is linked to mechanical sparking. So typically if your rotational speeds are less than 1 meter per second, mechanical sparking as an ignition source can be ruled out because it's slow moving. And of course, there's a whole range of information such as material of construction. So something could be non-sparking in materials like the bronzes, the bearing type, the types of seals, especially the electrostatic properties and the grounding system. So maybe some of the seals may be insulating, and if it's insulating, it could be electrostatically isolating. So that could lead to issues with static electricity. So usually when you undertake a NIRA, a typical recommendation could be that you may need to earth all your equipment, or do a check for earthing, especially if something's been dismantled when you put it back together. So that's one typical example. And the operating environment is also quite important in that aspect. So maybe your equipment is run in short batches, so it might allow a degree of cooling. So it could be a potential safeguard when you have to fill in your tables. Yes, and the drawings are important. So just to know that what are the clearances between, say, rotary equipment and the outer casing or the outer walls, and what mitigation systems you have. So, for example, you could have a reactor with a water-cooled jacket. It may provide a degree of cooling in the inside. So this is all that, try to get as much information when you're just about to start your NIRA. Procedural information, so operating, maintenance, the records, just to make sure. I think to note is that sometimes maintenance is undertaken by an external contractor. So I know from experience a lot of dust collectors are handled from external contractors usually, and better to have the records. At least they know in the records it will say what steps do they take. Do they do a general integrity check? Do they check the bearings? Do they replace the bearings? Sometimes it can be lost in that, so it's always good to have this type of information. Also, yes, manufacturer instructions. So this typically can be found in the manuals. So in your legacy equipment, it may tell you, oh, you may need to grease the bearings at so much intervals or every 100 hours or such. So this is important. So as I mentioned, why go look at the equipment? I think there's a lot of points out there, but yes, signs of damage, loose guards. Sometimes when you go look at it, it may be different from what you may see in the manual or the equipment drawings. So there might be modifications. It's just better to capture it. Maybe some ingress systems are not in place and not maintained as efficiently. And again, yes, it helps assess the consequences of ignition. So here's just a simplified version of the table, the risk assessment table it mentioned in the standard. So typically you outline your ignition source, and then you outline the scenario, so bearing, surface, temperature. So of course this is very simplified, and then you outline what measures you have in place. So you lubricate it, you have general maintenance, you may have the speed of it, you may have there might be recommendations to come out of it. So even in the standards, the 8079 standard, it gives you it gives you the steps to undertake to have a safeguard against a certain ignition source. For example, you could do load testing on your hot surfaces, so you can actually prove that when the equipment is run at load, or say 110% load at certain time intervals as evidence, and then you can show that this temperature never goes above or close to the ignition temperatures with a safety factor. So that's why I guess it recommends to verify surface temperature. So identify ignition source, find out the ignition relationship. So the normal operation, expected malfunction, and rare malfunction. This is a function of the zone classification that it is. This is scenarios. You typically put your scenarios in there. Just the guy word. And there's the findings. So here are just some examples of when you have to go into these legacy equipments, the things that you see there. So as you can see, there's a drive system, there's a belt pulley system, and these are all potential ignition sources, and there's scenarios you have to consider. So bearing could fail, the belts could slip, there could be a loss of lubrication or over lubrication, or maybe the lubrication medium is the wrong one they use. Is there any consequence of that? Maybe there's no. So when I say consequence, I mean it in terms of ignition sources becoming effective. There can also be over lubrication. There could be other things to consider. For example, static electricity. Probably not mentioned this. Maybe the belt is not anti-static. It can be isolated, and it could produce small sparks. And maybe this equipment is in a vapor atmosphere, so it could be a potential ignition source. So a recommendation on this photo, I definitely recommend maybe they need to check if the belts are anti-static, if it's in a vapor zone. So hot surfaces, typically you have temperature monitoring. Maybe there's an automated system that you have an alarm, maybe it cuts off after a certain temperature. There can also be hanger bearings. So this is the purging of bearings with air or nitrogen. Probably not nitrogen, but that's a type of safeguard. There could be seal flush, periodic thermal imaging. That's more like taking thermography at regular intervals. Maybe there's a walkthrough with an operator. So this is the benefits of thermal imaging undertaken for your motors. Gives good indication if something's about to go to failure, and failure could imply that potential ignition source being created if like motor overruns. If this is one of the benefits of undertaking this. So for mechanical sparking, there's many types of safeguards you could have. They could be vibrational monitoring. They can also be inadvertent. There's other sensors that could act as safeguards, but they could be indirect sensors. So for example, if you have a screw conveyor, you could have a blockage sensor, but that could also help you. It could also be used to detect something. Its primary function is to detect blockages, but ultimately it could help in other features such as hot surfaces. Maybe the blockages leads to hot surface or mechanical sparking. So yes, vibrational monitoring, component replacement within rated life. I think that's more referring to like bearings. So usually some clients may use bearings and until failure, or certain equipments are run to failure. This is talking about as a typical safeguard, you could have this. Yeah, here's a bathtub curb for bearings failure. So usually when the bearing starts to fail, it fails very fast in the short amount of time. So that's why you have to replace it within its useful life. So usually in NIRA reports, they recommend, or we usually recommend to have a suitable schedule of replacement. Also, I just want to add, now that we're in the webinar, if anyone has any questions, feel free to put it in the tab on the right-hand side. Yeah, oh yeah, I've got some questions. So I will answer it towards the end of the webinar. Okay, good. So yeah, it's a bathtub curb, just to show you the importance of replacing bearings at regular intervals. For dust, yeah, the static electricity is the next ignition source. So usually you have to ground everything, make sure everything is has electrostatic continuity to earth. Also propagating brush discharges. So sometimes you may need to know the materials of construction. Maybe you could have a belt, maybe it's insulating. Oh, sorry, it has two conductive materials, but maybe it might have a small layer of paint that, if broken, it could create a propagating brush discharge. So again, as I mentioned, so documentation, you need to know the hazardous zones, the flammability data, the completed templates. This is the risk assessment tables. Action list, responsible for the action. So this is like recommendations that come out of it, as you would in any risk assessment. So yeah, the NIRA is a live document. It's kind of like a DSIR. Well, it's like a DSIR, but like a micro level DSIR. So typically it should be reviewed regularly, every 2 to 3 years. I think 3 years is a good indication. And usually the NIRA is more specific, specific in the sense that your safeguards are specific just for your process. So when you buy an ATEX rated equipment, the equipment could be rated for a range of use cases, whereas the NIRA is more specific. So as I mentioned, like when you write in your safeguards in your tables, you might say, oh, my process is only run in batches, that this allows a degree of cooling, which is a safeguard against hot surfaces. So it's more specific, it's more, yeah, it's specific in that sense. A review is required when changes are made. So if you have new materials that with more onerous temperature, allowable temperature, so maybe the allowable temperature has gone down a little bit, maybe it's much more onerous, therefore there should be more safeguards, or safeguards need to be reviewed, and hence the NIRA review. So yeah, now I'd like to go through an example of a mixer. So basically, yeah, the step is in the standard, it gives you an example or a template table and how to fill it up. So as you mentioned, identify ignition source if it's effective, identify the scenarios with reasons. So each ignition source, there's a scenario that makes it effective, and then the typical the safeguard you outline, and outline any weaknesses and improvements. So this is the recommendations that usually come out of it. So yeah, step one, what ignition sources are there, and what are the examples? So for example, frictional heating between the bearings or static material, or a bearing failure, which could, some scenarios overlap each other, especially hot surfaces and mechanical sparking. So they're linked to each other, they're very similar. So the scenarios are similar, and they produce different types of the two ignition sources. It can make it very hot, or a spark can come out of it. So here's that first example. Here is a planetary top-mounted mixer unit. It's on a wooden pallet. It's open-ended, and I think, yes, it handles both vapors and dust. And it has these zones. So zone 1's 21s, zone 2 and 22 external. So that's basically category 2 within the bowl, where this mixer blade contacts the bowl, and category 3 on the outside. So that's vapors and dust. So in category 1, or the zone 121, we consider normal and expected malfunction scenarios. External, you only consider normal operation scenarios. So for example, something that's not so rare, but it does occur. But I'll go over that. What are the scenarios? So this is when you had to fill in your risk assessment table as per the standard, which we'll talk about in a second. Just see, yeah, there we go. So first you could break it down to ignition sources. As I mentioned, yeah, there's 13, then there's 4 in common, but unsuitable electricals you don't consider. So the first step I look at is where the hot surfaces could be. So there could be heating of the drive system, heating of the product by mixture. So in this bowl, it could contain some powders. Maybe there's some transfer of heat if it's come from a hot source. There could be conduction of heat from the motor to the bowl. So maybe if it's motor driven within that casing unit, maybe it can transmit heat through the shaft, through the blades, and into the explosive atmospheres. So for example, the vapor space, maybe that could heat it up. So it's a potential scenario. Whether it's effective or not, that's what you put in your table. Say, what are my safeguards? And that's why you could never, or sorry, not use the word never, but it's why it's not effective, it's not credible or not likely. Yeah, there could be a lack of lubrication. So maybe the motor doesn't have the lubricant and it gets a little bit hot and it conducts the heat into the shaft or into the vapor space of the mixing bowl where the flammable atmospheres are. Oh, the bearings could deform, can misalign, the shaft could start sparking. So what do I say? The blades, the shaft misaligns and then the blades hit the outer casing of the mixing bowl. So these are the scenarios to consider. There can also be a control system failure. That's probably if the mixer is running overspeeds or the loads, and that might have an effect on all the components. Say, for example, the seals, the bearings might get just a little bit heated. And so these are just examples you put in. Again, mechanical sparking, they could be trapped metal, they could be rust. Trapped metal could be even in the infeed. So when this mixing unit is being fed in, it could be some things that could be maybe lack of quality control, maybe some metal bolts got into the powder being decanted into this mixing unit. That could be a potential ignition source if it was to be agitated and the trapped metal hits the outer the outer walls of the mixer unit. That could create a spark potentially. The bowl, agitated misalignment, yep, we talked about that. Bearing collapse, speed controller failure, as mentioned previously. So yeah, static electricity. I think the first obvious one is that it's on a wooden pallet. Wood can be insulating. So insulating and isolating. So there's no continuity to earth in that aspect, and therefore this mixer unit is kind of hovering in air, and it may have a charge differential. So it could release a spark discharge as an example. Let's see, conductivity of lubricating oil. Maybe the oil might be exposed if it's not, although you can't see it on the mixer unit, maybe it's exposed and the vapors can ingress inside of the mixer, the casing of the actual mixer and contact this, and maybe that can create a spark. So yeah, typical safeguards would be, yes, procedure, so operating and maintenance procedure. It could be, yeah, instrumentation, maybe there's temperature monitoring, vibrational monitoring, earthing systems. I'd say like an earthing clamp, you can get one with a light, it tells you there's an interlock. Other safeguards can include ventilation, so sometimes an instrument is used outdoors and there's extra ventilation just to dilute it or extremely dilute, say, flammable atmospheres. But these are the typical safeguards you have, and improvements do include this in the NIRA risk assessment table. So this is in the standard. You have this table. It gives a template. So you outline, you fill in the table, and you put in each. So for normal operation, say discharges from isolated conductors, it's possible. Then so step one, you outline the ignition source, which is, say, static electricity. The description, so what is the scenario? What is the cause? So it could be isolated conductors. And then the reason, you outline that. And then you outline the descriptions of measures applied. And the table 3 with ABC has the different bases of the references. So you could reference technical standards. So for example, you can reference the Statics Bible, 6079-32, and it may say this is the allowable surface area. So you could put your references there. You could also put your references for example, operating procedure, so internal documents. Say you could reference PPM procedure, this is the work order number, this is the template. So this is how thorough it is. And then you could move the frequency with the measure applied. So it moves to the left or to the right, so to the left, and then it gives you a resulting equipment protection level. So this is just an example, but this methodology is very well described and explained much more great detail in the standard. So yes, to summarize this webinar, we've had a background to ATEX rated equipment. We've understood the risk assessment procedure to classify, more specifically designate or say self-certify equipment that they are suitable for use in hazardous areas. So that's the key point. So if an incident does occur at your site and you have this document, this risk assessment table, it can be shown to say HSE inspectors, and it can be used as a basis to show that it is safe. How to prepare for a NIRA, so what things to look out for, ignition sources and example scenarios, which is, yes, the tricky part, the safeguards and improvement in recommendations. So this is what comes out of such a webinar. So what comes out from a non-electrical equipment ignition risk assessment, a NIRA, which is the technique. And that can be applied to, as I mentioned, a range of equipments, typically mechanical equipments, but they can apply to low risk equipments like valves, even just surfaces, even just static pieces of equipment that like a storage vessel. You can use the NIRA technique on that to show that it is safe for handling, say, flammable materials. Of course, it is very specific. It needs a lot of documentation. So it needs, like, as I mentioned, manuals, drawings, operating procedures, records, everything. So and it has to be reviewed at regular intervals. So that's the procedure. Yes, so I just want to thank everyone for being part of this webinar. Also, just to mention about our company, if you have any questions or like to contact me, my email is there at info@sigma-hse.com. I'm going to just look at the questions. Might have time for a few. Can you carry a if you're not known flammable internal environment to be safe or not? So yes, so the question is, can you carry a NIRA without knowing if the material is flammable or not? So typically NIRA is the secondary process after you take the desir. So the first step when you go to site, you undertake a desir or in a desktop or with a site visit preferably. Then you have your hazardous zones. Then you know how big your bubbles are, and what equipment or ignition sources are there, and then you could isolate each equipment and then undertake this risk assessment, this NIRA, and that is the main procedure. So you go over that and you could show that an equipment is safe for use. Of course, the NIRA is only limited. It doesn't have the electrical aspects or the unsuitable electricals. It has its own standard, which is, I think, 6079-14 and 17, which needs another survey. It needs, because as you know, there's different types of protection for electrical equipments, such as different types of sealing especially for vapor environments. So yes, yeah, that's what I would like to talk about. Is there any more questions? I'll just wait a bit. Okay, seems like there's only one question. Just bear with me. There is a question, but I think my, oh wait. You see, see, I zoomed in my screen so much I can only just see a part of the question. Sorry. Just a moment, I'll just ask. Oh yeah, here we go. Okay, if using thermography, how do you prove internal temperature is not too high? When I say thermography, I meant more from the outside, like usually use thermography for for motors. It gives a basic indication that something is not right. So you could use thermography for external equipment, but in terms of specific internals or areas, you have to do testing. So temperature testing, load testing, which is outlined in the standard. But the thermography is a good safeguard as a general high level. Say, for example, you could take thermography of the equipment, say the outer motor or the shell of the body of the equipment. At least it gives an initial indication that something is wrong, so you could stop it and then not allow the ignition source to get ahead. Sorry, to progress and become effective. That's the right word. There's one more question, I think. Okay, yes. Is there a procedure for low energy electrical items like the use of mobile phones in use in hazardous areas? As you mentioned, electrical items, yeah, so they, as I mentioned, they usually have their own standard for ensuring compliance, making sure they're acceptable for hazardous areas. But because the size of these equipment, such as the mobile phones and smartwatches, it's usually linked to the zone that you're in. So if you're in a zone 0 or 1 vapors, then I wouldn't be using that in hazardous areas. And it's better, sometimes it's better to replace them with ATEX rated electricals than to undertake a NIRA. NIRA is usually, as I mentioned, for the larger equipments. It can be used for small, the technique can be used for small equipment, but more the larger equipments that more specialized, typically in dust handling environments more than vapor. But yeah, that's the procedure. It's easier just to replace with ATEX electricals, for example, smartwatches and such, than to undertake a NIRA risk assessment on it. Yeah, that's my answer. Is there any more questions? I think there was only the 3. Okay, here's another one. Here, sorry. How do we deal with materials online which are not causing vapors or are a dust but can catch light? So the NIRA is more for, it is in connection, is linked to from flammable atmospheres, which is linked to DESIR. So you have to test your material first, and if it's going to create this flammable atmosphere, which could be ignited, then yeah, then you can undertake the NIRA on that specific equipment. But you have to look at it from a case-to-case basis, and it depends on what equipment it is. Because you mentioned the line, so it could be a production equipment, it could be, is it a large mechanical equipment? So NIRAs, as I said, is usually associated with mechanical equipment, non-electrical, as the name suggests. So my answer to that is you have to get your material tested, but can catch light. There are some materials that have different legislations, like explosive regulations if you're handling pyphoric materials. But the NIRA technique is good in that aspect. I have one more question. Sorry. Oh yeah, sorry, only the 3 questions. Is there any more questions? Feel free to send it to me via email. I'm happy to answer it and help out. Okay, thank you everyone, and I hope to join you in the next webinar.